Okay, so I think that it's about time to start. We have today 2 lectures, as most of you have seen probably. Nice thing is that both of them are actually Blackboard lectures today. The first speaker is David Garfinkle, who is going to talk to us about numerical general relativity. You come from Oakland University,
right,
in the United States.
That's
so
right.
Please, David.
Thanks very much. Okay, so I've been assigned the task to give a sort of somewhat general and introductory talk to the subject of numerical general relativity. So I want to start by saying that from the point of view of numerics, this is kind of an odd subject because usually in numerics we have, some set of equations that we've sort of known forever, and the question is, what is the fastest, most efficient, most accurate numerical method that we can bring to bear on this set of equations? In general relativity, it's a little bit different because a whole bunch of time and effort gets expended on what form shall we put the equations in. And once you do that, you find that, well, a whole bunch of fairly straightforward numerical methods work just fine, although then you can ask the question of, well, if we choose this numerical method rather than that numerical method, maybe things will go a little bit quicker or use a little bit less memory. But most of the effort gets expended on what form shall we put the equations in, and I will explain why that is in a little while. Okay, so, but first, right, since I'm not supposed to assume that anybody knows anything about general relativity, I'm supposed to say what that is first, and then talk about the numerical issues. So, for those of you who already know Riemannian geometry, the easiest way to introduce the subject of general relativity is to say that general relativity is just like Riemannian geometry, except that the metric is not positive definite. But for those of you who don't already know Riemannian geometry, let me start at the beginning. So the basic idea is that in general relativity, we draw a bunch of space-time diagrams. That is, we draw pictures where, for some unknown reason, time goes in the vertical direction, space goes in the horizontal direction, and what we're drawing is histories of things. So this is, say, a person in the middle of this room now. This is, say, a person in the middle of this room an hour later, and if they just sort of, stay in this room like this, then their history, their world line looks like that. If, they're sort of very restless and they get up and walk around the room, their world line might look like this. And if, sort of 5 minutes into the talk, they get disgusted and go somewhere else for a while, and then, sort of come back for the next talk, and the world line might look like this. But in any case, the basic idea is that you just sort of draw these trajectories. Okay, so now I want to introduce a sort of slogan associated with general relativity, but which you don't really hear very much, but it kind of encapsulates a lot of the subject. Okay, so the slogan is clocks are like odometers. So remember, the odometer is the thing in your car that tells you how far you've driven. And remember also that if you, are in your car and you start at point A and you drive and you get to point B, that's not enough information to tell how much mileage has elapsed on your odometer, because there are lots of different ways to get from point A to point B. So what general relativity, and in fact even special relativity, tells us is that if we have a world line, that is a person at a particular time, and then at some time later they're at some particular place, and if this is the curve that is their history, and starting from here and going to there, that we have a rule that tells us how much time elapses on the watch that they carried with them. Okay, so what is this rule? Well, the rule is that there is some metric, some symmetric tensor of type 0, 2. You can think of it as being like a 4x4 matrix, and it has some dependence on the coordinates. And if we want to find out the amount of elapsed proper time, we use the following formula. So the curve gives the space-time coordinates as a function of some parameter lambda. And now if we do the following integral, then this gives us the amount of proper time that will elapse on the watch of the person whose trajectory is this. Now, I want to just call your attention to a couple of features of this formula. So first of all, you might worry, well, I mean, given a curve, I can always reparameterize it, but this elapsed proper time, delta tau, is supposed to be a property of the curve, not about which parameterization I chose. But you can easily convince yourself, two easy lambdas. You can easily convince yourself by counting the d lambdas that this is parameterization invariant. The second thing I want to call your attention to is that other than this minus sign, right, this is exactly the formula for length of a curve in Riemannian geometry. So this is why, general relativity is basically just like Riemannian geometry, only with these funny minus signs. Okay, so let me give an example.
Ask a quick question.
Sure.
Are you considering t to be one of the x's?
Yes.
Okay.
Definitely, right. So in the space-time diagram, there are 4 x mu's, t, and x, y, and z. Yeah. So in the absence of gravity, the metric just has the following form. Where the i's are the ordinary spatial x, y, and z, and all the other ones are 0. And so then this formula becomes that delta tau is equal to integral from a to b d lambda of dt by d lambda squared minus x by d lambda squared to 1/2. So here's a difference with Riemannian geometry, right? So, and I should mention also that to make the units come out right, that I am choosing units in which the speed of light c is equal to 1, and so this is why I can have sort of t having the same units as x. You can think of this t as being ct if you want to sort of put the c's back in. The other thing to notice is that in order for this to be an actual real quantity, the stuff inside the square root has to be positive. In other words, dx by d lambda has to be smaller than dt by d lambda. That's just another way of saying that this is a history of someone who is always traveling slower than the speed of light. So in other words, this formula for elapsed time is only supposed to be taken for trajectories where people are traveling slower than light, but that's okay, right? We don't get to travel faster than light. And then one puts in this formula and you can calculate the elapsed time. Notice also another difference, though, with Riemannian geometry because in Riemannian geometry, if I were calculating length, there would not be any relative minus sign, and so things would add, and so what that would mean is that, you know, by wiggling things around, I could always make curves curves longer. Here it's exactly the opposite. Now, if, for example, you know, sort of standing in this room, you get impatient, you decide to run back and forth really fast, then what you'll find is that the elapsed time on your watch is actually a smaller amount. So in Lorentz geometry, by sort of wiggling curves a lot, you actually make them shorter in terms of elapsed proper time rather than longer. So in contrast to Riemannian geometry, where you can ask the question, you know, given points A and B, what is the curve of shortest distance between them? In Lorentz geometry, you ask the opposite question. Given points A and B, what is the longest possible distance between them? Yeah.
So this is this only a measure of time, not
Yes.
space?
Well. So the idea is, I mean,
So if you move at the speed of light, your delta tau is 0.
yes.
Okay.
Yeah, that's right. Right. So you want to think of it as, I mean, so in Riemannian geometry, we have this metric that tells you what length is along a curve. And now in Lorentz geometry, we have this metric that tells you how much elapsed proper time is given along curves that represent the history of observers traveling slower than the speed of light. Okay, so now let's think about, so this is a theory of space and time, so that's all very well, but general relativity is also a theory of gravity. So the question is, where does gravity come into all this? So let's see. It's the easiest way to do this. So I should put this up here. Okay, so where does gravity come into all this? So basically it comes in the following rule. Did I lose some light?
If you lift it a little bit, the light will come back up there.
Oh, I see.
Yeah, when they're both down, I think you're ready.
Oh, I see, okay. Oh, so that's affecting the light that way. All right, so sorry. All right, let me do it this way then. Okay, so the basic idea is that in free fall, that is, if an object is acted on by the force of gravity and no other forces, then the rule is that what it does is it moves along a trajectory that is the maximum of proper time between those 2 points. Or put another way, this proper time is, given by this metric is now the action for an object acted on by gravity. Okay, so now we're in business, right? Because we remember that if we have an action and we want to maximize it, that, you know, we just write down the usual procedure and we get the Euler-Lagrange equations, and then, you know, we can forget about, you know, this quantity we're maximizing and just say, great, we're going to solve the Euler-Lagrange equations. Okay, so how does an object move in free fall? That is, what are the Euler-Lagrange equations that correspond to this action? The answer comes out as follows, and let me write it in a couple of pieces. So let me start by saying that it's exactly the same equation that you get in Riemannian geometry when you ask what is the curve that minimizes length, because you're basically doing the same calculation, you know, other than this minus sign. Okay, but anyway, here's the answer. So the answer is that the four velocity, that is the tangent vector to this curve that's the history of this person, satisfies the geodesic equation. So let me explain to you what each of the quantities in this equation mean. So u alpha is the tangent vector to that curve, but not just any tangent vector, it's the unit tangent vector. So in other words, the parameter now is not just any old parameter, it's the actual elapsed time on the clock. And this grad alpha has one piece that's just plain old ordinary derivative with respect to the coordinates. And then another piece, which is a little bit messier, where this sort of ugly looking piece with the Christoffel symbols I will write out in gory detail. So basically, just by using the inverse metric and the derivative with respect to the coordinates of the metric, you can calculate these Christoffel symbols, and then you plug them into this equation, and this tells you how objects move in free fall.
So this is exactly the same as expressing the connection in Riemannian geometry.
Yes,
in terms
yes,
of
it's exactly the same.
Yeah.
Right, so this
But the
covariant
minus sign-
derivative is basically the Riemannian geometry connection, and this is the geodesic equation, just exactly like in Riemannian geometry. So even though there's this funny minus sign, you can calculate things. I mean, you know, the whole calculation works exactly the same way it does in Riemannian geometry, and you get exactly the same equation. And also, in addition, right, you don't have to take my word for it because you know what the action is. And so you can just say, oh, well, this is the action. And so I know calculus of variations, and so I'll just vary it and get the equation. And when you do that, sure enough, you find that this is the equation again. Okay, so so this metric, right, is very important in general relativity because it's the thing that tells us how objects move in a gravitational field. Given, you know, some situation, if we can work out what the metric is, we'll know what the gravitational forces on everything are. Okay, so now I want to call your attention to one sort of property of this covariant derivative, this connection. So remember that if it just had this piece, that is derivative with respect to the coordinates, since we know that you know, plain old ordinary partial derivatives, it doesn't matter what order you take them in. If we didn't have this extra piece, then it wouldn't matter what order we took, you know, two covariant derivatives in. But because we do have this extra piece, it does matter. So let me write down what the consequences of that are. Okay, let me switch my table. Okay, so suppose I take two covariant derivatives in different orders, and I take the difference. Okay, so if these were plain old ordinary partial derivatives, I would just get 0, but because we have these Christoffel symbols, I don't get 0, and in fact, what I get is the following. Where, since you have a formula for the Christoffel symbols, and you have this sort of thing that gives the relation between, you know, Christoffel symbols and ordinary derivatives, you could, you know, sort of work out exactly what this Riemann tensor is. I'm not going to write down for you the sort of formula in gory detail, but you can easily tell from the formula for covariant derivative and the formula for the Christoffel symbols, that the sort of structure has to be something like, it'll have a piece that's sort of derivatives of gamma and another piece that's sort of, squares of gammas. So this is basically how it goes, but I'm not going to, sort of put in all the indices. Okay, so what does this thing, what does this Riemann tensor mean in terms of the physics of things falling in a gravitational field? Well, basically what it does is it gives the relative acceleration of things that sort of start out falling in the same direction. So there's a formula that basically says that if I, sort of drop two objects, not quite at the same place, then their relative acceleration is basically going to be a particular component of the Riemann tensor dotted into their sort of relative distance. So let me just draw a picture to illustrate this. Okay, so imagine that I'm high above the Earth, and I drop 5 marbles in the following configuration. So then the question is, what is this configuration of marbles going to look like later, right? What is going to happen to this shape? So you might say, you can't fool me. I remember learning that all objects fall the same way in a gravitational field, so surely, this configuration of marbles won't change. And that's close to the truth, right? Things fall exactly the same thing in a uniform gravitational field, but the gravitational field of the Earth is not quite uniform. Remember, it falls off like 1/r². So let's look at this a little bit more closely. So suppose that this arrow represents the acceleration of the middle marble, right? Then the acceleration of this marble, since it's closer to the center of the Earth, will be just a little bit more. I exaggerate the difference here. The acceleration of this marble, since it's a little bit further away from the center of the Earth, will just be a little bit less. And for these two marbles on the side, remember that the acceleration points directly towards the center of the Earth. So these two accelerations compared to the one in the middle will be in slightly different directions, which I again exaggerate. And so now, if you look relative to the center marble, right? If I think of I'm just sitting on the center marble, so its acceleration is nothing. Then relative to that, so the other parts sort of look a little bit surprising, but follow clearly from this diagram. Okay, so this part, right? You're sort of clearly already anticipating, right? This has a little bit bigger acceleration downwards, so relative to the center one, it looks like this. But this one has a smaller acceleration downwards, so relative to the center one, it actually looks like that. In other words, this configuration of marbles is being stretched in this direction. And because of the directions of these things, relative to the center marble, this is being squeezed in this direction. So in fact, you can show that the amount of stretching, the sort of magnitude of this sort of stretching acceleration is in fact twice as big as the magnitude of the squeezing acceleration, in such a way that, if I also put sort of a marble here and a marble behind the board, the overall volume of the object wouldn't change. So this is sort of, in physical terms, what the Riemann tensor expresses. Okay, so now I want to write for you a couple of tensors related to this one.
So the position of these marbles to the left and to the right, they resemble an arc, which is exactly the arc of the Earth, such that they directly go towards the marble and not a little bit downstairs.
Well, so the idea is that,
So So
everybody has a trajectory that's pointed towards the center of the Earth, and with an acceleration that's proportional to 1 over the square of the distance to the center of the Earth.
so what is
So
the
I mean, I
exact-
exaggerate a little bit, you know, sort of the size of everything here, but the basic idea is that for a small configuration of marbles to sort of first order in, you know, size of the configuration divided by the distance to the center of the Earth, the relative acceleration of these is just pointed inward. In other words, these two arrows have just about the same magnitude as this one, but slightly different directions. So the sort of difference between the arrows just points directly inwards.
Okay, directly to the marbles. So is it a horizontal line? If I draw a line between the 3 marbles there,
Yeah.
is it a horizontal line?
Yeah. Okay, so now let me write down a couple of things related to the Riemann tensor. Okay, so there's the Ricci tensor, which is basically just sort of the trace of the Riemann tensor over 2 of these indices. And then there's the scalar curvature, which is, again, the trace of this quantity. All right, so let me explain why I'm writing down these particular tensors. I've told you that, well, once you know the metric, then you know how stuff falls in the gravitational field. But the question is, how do we find the metric itself? What is it that determines that? That is the problem that Einstein sort of wrestled with in the years leading up to the end of 1915, when he finally came up with an answer. And oddly enough, throughout 1915, Hilbert was wrestling with the same problem. And Hilbert, so they basically solved it independently and more or less simultaneously, although Hilbert might have beaten Einstein, you know, by a week or something. So I'm going to sort of give you both of their answers. So in a way, Hilbert's answer is easier to come up with, right? I mean, we're supposed to have theories that come from Lagrangians. Lagrangians are supposed to be scalars. The only scalar I see in the problem is this, so surely this must be the Lagrangian, right? So in other words, the Lagrangian for gravity is basically just this scalar curvature. Okay, but now, you know, given a Lagrangian, we want to know what the Euler-Lagrange equations are. And those equations are ones that you know, Einstein came up with, you know, independently without this sort of Lagrangian reasoning. Okay, so for vacuum, that is the case where there's no matter, and I'm just looking at you know, sort of a gravitational field in a region outside of matter. The field equations are just that the Ricci tensor is equal to 0. And now in the presence of matter, we get something a little bit more complicated. Okay, so in this case, this G on the right-hand side is Newton's gravitational constant, right? This is the relation between, you know, sort of matter and gravity, and this T alpha beta is called the stress energy tensor, and it's basically the thing that tells you, you know, what the energy density is. Okay, so now we're in business, right? Now we have field equations, and now in terms of computation, we can think about, okay, cool, you know, let's go ahead and put these things on the computer and see what they do. Okay, so what do the field equations look like? What are we supposed to do with them? Well, remember, right, that the Riemann tensor, and therefore all these contractions of it, are going to have the structure of derivative of Christoffel symbol plus square of Christoffel symbol, and okay, well, the Christoffel symbol itself has one derivative of the metric in it, and so these equations, you know, 10 nonlinear coupled partial differential equations, are at least going to have stuff that you know, involves some terms with two time derivatives. And so what we're supposed to do, right, is we say, oh, good, stuff with two time derivatives, that's an equation of motion. We put that on the left-hand side, everything else is on the right-hand side, and we get second derivative of metric is equal to stuff, and those are our equations. Okay, but before we go ahead and write these, well, and you know, throw them on the computer and see what they look like, let's ask ourselves, you know, well, okay, is this, you know, a mathematically well-posed problem, right? So in other words, what do the equations that you get by looking at this actually look like? All right, so let me switch back to words again. Okay, so the nice thing about, you know, sort of asking whether stuff is well posed is that you don't need to write down the whole equation. You just need to write down the stuff that has the highest derivatives. So let's, you know, think about the expression for the Ricci tensor and just look at the highest derivative stuff. And when we do, we get the following. Okay, so this is it, right? I mean, there's lots of other terms in the Ricci tensor, but they all have, you know, fewer than two derivatives. So this is the stuff that has two derivatives. So this first piece looks nice, right? I mean, this basically just looks like a wave equation. Wave equations are hyperbolic, and furthermore, we've got lots of computer methods that work fine on the wave equation, so we're ready to put that on the computer and go. But then there's this stuff, right? So this H is basically the sort of trace of the Christoffel symbol, but you know, it has one derivative, and now we're taking derivatives of it, so this has two derivatives, and this doesn't look like the wave equation at all, right? In fact, this makes the problem look as though it's not mathematically well posed at all, and we don't know what to do with it. Okay, so this was the difficulty that Ivan Shakeh-Burhat struggled with in the 1950s and came up with an answer. But before I tell you what her answer is, let me remind you that we've sort of seen something like this before, and let me remind you what that is and sort of how it's resolved. So we've actually seen behavior like this before in Maxwell's equations. So let me write that down and explain what happens. Okay, so one way of writing Maxwell's equations, you know, outside of charges and currents, is to say that, well, we have a two-form F that satisfies dF is equal to 0, and it also satisfies d of star F equals 0. If there are charges and currents, well, then they go on the right-hand side of this equation, but that won't matter for our purposes. All right, so how do we solve this equation? Well, we notice that if d of f is equal to 0, that means that f is equal to dA, where a is a one form, and now this equation just becomes d of star of dA looks nice. And now what happens when we actually write that down? Okay, so what we find when we just write down Maxwell's equations in this way is that we get this piece that looks like the wave equation, and then this piece that doesn't, right? And looks like and so now if I write the whole equation together, this doesn't look hyperbolic, it doesn't look well posed, it doesn't look like something you can do anything with. Okay, so it turns out though that this is actually a feature, not a bug, and the reason is the following. To make these equations simpler to solve, we've introduced this vector potential. But remember, if I have a one-form A, and I change it by A goes to A plus d chi, where chi is a scalar, then this doesn't change F at all, right? And so this new A is just as good a solution as the old A. And so what that means is that writing the equations in this way, they're not supposed to tell me what A is given initial data, because there are lots and lots of different A's that could satisfy this. So yeah, the equation in this form is ill-posed, but it's supposed to be, because there's no way that that initial data for A should have a unique solution. It doesn't. All right, so how do we fix this up? Well, the ability to change A in this way, that is to change A under a gauge transformation, allows us to choose a gauge. And in particular, we can always choose a chi to make A so that d alpha of A alpha is equal to 0. And having done that, this goes away. And now we're just left with the wave equation. And so being left with the wave equation, we can go ahead and solve it, and everything's fine. All right, so great. So now I can explain to you Ivan Shatkevich-Pat's trick for showing that general relativity is well posed. So if I have a coordinate, if I have a set of coordinates x gamma that satisfy the wave equation, then they also satisfy h gamma is equal to 0. So in other words, I can choose a gauge that actually makes these bad terms go away. And then when you've done that, you find that what's left, just looks like the wave equation, and you can solve it using hyperbolic methods. Okay, so now so you would think, right, since Shatkevich-Pat's theorem dates back to the 1950s, and since we have lots of numerical methods that work with the wave equation, that everybody doing numerical relativity would be using these harmonic coordinates. But in fact, for decades they weren't. And I want to explain why, and then I want to explain how people came back to them. So you sort of look at this and you say, okay, this is cool. I'm just going to solve Einstein's equation this way. But when you do this, you're committed to the fact that your time coordinate is a solution of the wave equation. And let me explain why this can create difficulties. So suppose your time coordinate is a solution of the wave equation. Remember that, so now the surface of constant time looks like this. But remember that surfaces of constant time can't be any old surfaces. They actually have to be time-like surfaces, otherwise the problem is not well posed. So if I get a surface where at some point the tangent vector is traveling at the speed of light, then all of a sudden this problem becomes ill-posed. And so the idea is that it's not enough to just say, okay, the equations look good. You also have to ensure that your time coordinate remains time-like. So this problem was sort of solved a while ago by Helmut Friedrich, And what he did was to say, all right, suppose instead of having a solution that's a solution of the wave equation, I put in some source function that can depend in an arbitrary way on the coordinates and even on the metric, although not on the derivatives of the metric. So now if I do that, these extra terms here will add things to the equation, but not add the order of two derivatives. And so this won't destroy hyperbolicity, but now if you somehow manage to choose these gauge source functions cleverly enough, you can do it in such a way that you can arrange that your surfaces of constant time always stay time-like, and the problem becomes fun. So now the harmonic coordinates with these gauge source functions is the basis of lots of different numerical relativity codes, including one that worked for simulating binary black holes. Yeah, you got a question?
So your square just a standard wave operator, or does it depend on the method?
No, this is actually the sort of curved space-time wave operator. So this is really this. Okay, and then when you do that, if you write this curved space wave operator in terms of ordinary derivatives and Christoffel symbols, you can find that setting this equal to 0 is equivalent to setting that equal to 0. Yeah.
Okay.
So this is not the flat space box. This is sort of curved space box.
And your like grad alpha is some sort of like surface grid.
Well, so the idea is so taking one gradient, right, is just an ordinary derivative. So in other words, this is equal to let's say d alpha gamma. Let's see. Okay, so these are sort of covariant derivatives, but taking a covariant derivative of a scalar is just the same as an ordinary derivative. So I get one thing that's two ordinary derivatives and then one Christoffel symbol, but because these are supposed to be the coordinates, right? D, beta of x gamma is just the Kronecker delta. So two derivatives give 0, and this gives a Kronecker delta, and this quantity just gives h. So what you're doing is you're choosing the coordinates to be solutions of the curved space wave equation, not the ordinary, flat space box. Yeah.
So you've got a mesh on space-time that's like your artificial coordinates, and then you're solving for the x's and the g's simultaneously on this mesh.
Well, so this is just one way of showing that you can actually solve this, but in fact, once you put the equations in this form, you can sort of forget about I'm actually solving for the x's. You can just say I'm just solving for the g's. I mean, you could reconstruct the things later, but yeah, all you're really doing is solving for the g's. Okay, so let me actually mention now, since time is short, two other problems in numerical relativity that have been tricky, but we have ways to deal with them. And then we'll be done. What have I got, about 7 minutes or something?
Let's see, yeah, something like that, 6 minutes.
Yeah, okay. Okay, so the first thing I want to mention has to do with constraints in general relativity. So let me use this abbreviation G alpha beta to be, this sort of thing that's the left-hand side of the Einstein equations with matter. So I said in general, sort of looking at things, we figure that they should have two time derivatives. But in fact, if you look at the stuff that is the component in the time direction of this tensor, you will find that it contains at most one time derivative. And so what that means is that these particular components are actually constraint equations, not evolution equations. And this is also familiar from Riemannian geometry, where these things are called the Gauss-Kadazzi equations. So what that means is that in general relativity, you don't get to choose the initial data freely. You have to satisfy certain constraints. Although that too is familiar from Maxwell's equations, right? In Maxwell's equations, we can't just choose any old B. We have to choose B where div B is equal to 0, and in the absence of charge, we also have to choose div B is equal to 0. For Maxwell's equations, you don't have to solve the constraint equations at every time step as long as you satisfy them at the beginning. The evolution equations preserve them. The same is true for Einstein's equation. However, and again, this is sort of something that's familiar from Maxwell's equations, but it's much, much worse in general relativity. It's true that analytically, if you solve the constraint equations exactly, and you implement the evolution equations exactly, then the constraints will remain preserved. However, in a numerical implementation, you're solving the constraints approximately, and you're implementing the evolution equation approximately, and that means the constraint violation will grow. And in fact, for a lot of implementations, what happens is that the constraint violation grows enough to basically make the solution completely inaccurate. And so sort of what do you do? The answer, it turns out, is that because you have these constraint equations, you're free to modify the evolution equations by adding any multiples of the constraint equations to the right-hand side that you want. And there are particular sort of sneaky choices of this that will allow you to evolve in such a way that constraint violation damps rather than grows. And so this is sort of a tricky problem, but with a workaround. All right, finally, in the last couple of minutes, I want to mention a problem that's sort of peculiar to general relativity, although in principle, the sort of solution is something that we could use in other areas. And that has to do with the properties of black holes. Okay, so a black hole is basically a region in which gravity has gotten so strong that even light can't escape. So now imagine that you have some object, some matter that's somehow gotten itself sufficiently compressed that it's formed a black hole. So this dotted line is sort of the region of no return. Everything inside it, is going to be trapped. Okay, but now things are even worse, right? Within the black hole, to stand still would amount to traveling faster than the speed of light. And so this matter that has somehow gotten itself compressed enough to form a black hole must continue to shrink, and eventually all the matter will sort of fall into the center, and we will have a point of infinite density and an infinite space-time curvature. Okay, so now, when you're doing a simulation, what are you supposed to do with this? So now if I draw a space-time diagram, here's the singularity. This dotted line is going to be the event horizon of the black hole, and these are my constant time slices. So if a constant time slice ever hits the singularity, it's game over, and we stop. So you have to somehow keep the constant time slices from hitting the singularity, but if you slow them down inside the black hole and move them at normal speed outside, your numerical grid is going to stretch a lot and you will lose accuracy, and so what do? And so the answer is something called excision. you just cut out the inside of the black hole from your numerical grid and just, evolve out here. And so now you think, oh, well, this is terrible. I'm ending my grid right here. What the heck am I supposed to use for a boundary condition? But this is the cool thing, because everything travels at speed slower than the speed of light. What that means is that at this boundary, you actually only have loads that go in this direction. And we know for hyperbolic equations that when that happens, not only do you not need a boundary condition, but you're not allowed to use a boundary condition. And so you use no boundary conditions at all, and it works just fine. Okay, so I think I'm out of time. So thanks very much for your attention, and thanks for inviting me to give this talk.
Somebody wants to ask a question, David?
Yeah.
You give the impression that everything is fine. So what are the issues? What kind of research projects people are interested in?
Okay, so I should mention, first of all, that I mean, a lot of these issues, how do you get the equations in the right form? How do you, get hold of constraint damping? How do you go ahead and do things in such a way that you don't have to worry about black holes? These were all geared to, sort of how do you collide black holes and in such a way that you can get out the waveforms of gravitational waves produced by them in order that you could compare these to the measurements of LIGO and the other gravitational wave detectors. So that problem was finally solved in 2005. And so now, if all you're doing is colliding black holes, then I think we're basically done. However, now there are sort of other things that make gravitational waves as well. So you can collide neutron stars with each other. You can collide a neutron star with a black hole. You can look at gravitational waves produced by supernovas. And now all of a sudden, you're left with things that are more usual types of numerical problems. So for example, you're left with the question of what method do you use to sort of make things more efficient. So this sort of thing works fine using plain old ordinary finite difference codes, but maybe you can get your codes to run a lot faster if you use spectral methods or if you use Galerkin type methods. And so so there's the whole sort of standard numerical issues of what do we use to get things to be most efficient. If you're only colliding black holes, you only have to do the vacuum Einstein equations. But now if you're colliding a black hole with a neutron star, now you have to solve the Einstein equations with matter, and the matter has to satisfy its own field equations. So now you have fluids, and fluids can shock. You need a good shock capturing method that also plays nice with general relativity. You have neutron stars have enormous magnetic fields. You need to do magnetohydrodynamics. Neutron stars have lots of neutrinos. How do you deal with neutrino transport? In principle, you want to solve the Vlasov equation, but that's outrageously numerically expensive. Is there any good sort of approximation method that you can use that doesn't require you to solve Vlasov but still gets things accurate enough? So in some sense, the open problems are closer to sort of standard numerical problems, but they're all of the form. How do we get what we do in other contexts to sort of play nice with what we do in general relativity. So that's those are sort of more of the ongoing problems.
All right. I think maybe okay. I think maybe we should stop and maybe we could just have a break and then maybe continue with it if that's okay. So I suppose we thank David once again.